Alright, so today I'm presenting one of our works that we are doing in our lab together with Keisuke, one of our PhD students. This is a talk that I borrowed from a Google Tech talk that I did in February, and that was related to 3D perception from SLAM. It's a bit longer than the time that I'm allowed today, so I'm just gonna make it a little bit short, also because we have a live demo afterwards from Keisuke. But let's say the main goal and the main topic is how to extract semantic information from SLAM and for 3D reconstruction. First of all, a brief introduction on our group. I'm currently working as an assistant professor at the University of Bologna, but I'm also coordinating the computer vision group at the chair for augmented reality and computer medical image analysis at TU Munich under Professor Nasir Navab. And the computer vision group currently has around 6 to 7 PhD students and several collaborations with industries such as Google, Toyota, Canon, BMW, Carl Zeiss. The main core activity of our group is 3D perception and 3D computer vision. So for this reason we use PCL for our, let's say, current activities, because of course there's a lot of very useful tools available in PCL that we can use for our goals. We also work in the field of augmented reality and medical image analysis, because that's kind of the core of the entire department, of the entire chair. So the computer vision group kind of serves as a way to develop new machine learning and computer vision algorithms for that kind of applications. We're very focused on RGBD perception, so we use a lot of these sensors like the Google Tango, the Kinect V2, and also these sensors that are now more for embedded architectures, such as part of the Tango, also the structure. There's new sensors coming out that are more and more mobile, which is of course more and more challenging for perception, because it means that you have to have algorithms that work in all sorts of unstructured environments. They have to be extremely efficient because of the embedded architecture. So it's a lot of challenges for computer vision people. We developed in our past a lot of algorithms which were also partially ported to PCL. I personally worked a lot on key point detection and description. This is a work that I presented at CCV, where the main idea is to use a random forest to learn how to pair a key point detection to a key point description. In general, let's say I also contributed to PCL mostly in key point features and recognition modules, and I also built a stereo PCL module. So in particular, for example, there are descriptors such as the one that we call unique shape, context, and shot that are currently available and that can be used for different 3D perception tasks, such as point cloud registration and object recognition. This is a recent work that they did in this regard, which is related to object recognition from point clouds under very severe levels of clutter and occlusion that they did together with Aitor Aldoma, a PhD student from the University of Vienna who's currently working for Apple. And this code is also currently available in PCL. There's also a tutorial if you're interested to have a look at that. This is not the only, let's say, perception task that we are currently trying to solve with some other students, like for example David down there, another PhD student in our group. We're working on 3D object detection and tracking from depth views. This is one of some of the results that we got so far. So this is the 3D tracker that we developed that runs in real time on a single CPU core from just by using depth data. The focus of this talk is actually on SLAM. So the main idea, which is also the main topic for Keisuke's PhD, is how we can somehow leverage this additional information that we have when we reconstruct the environment, for example using SLAM or Kinect Fusion, in order to extract some kind of semantic information that is way richer than the information that we can extract just from a single view. So there have been like a lot of, not a lot, but let's say a few recent approaches in the past 2 or 3 years, trying also to do something similar. So leveraging standard SLAM techniques, like for example LSD SLAM, which is currently the state of the art for monocular SLAM, or for example this dense RGB SLAM, which is instead a very good algorithm when you also have that data available, and try to use this kind of reconstruction framework in order to get semantic information. Maybe the first work is called SLAM++. The SLAM++, the idea is to do jointly SLAM reconstruction and object detection. In this case, the idea of the work is that SLAM reconstruction can have object detection, because once you detect an object in a certain position, once you move from another viewpoint, you can use the SLAM in order to remove the part of the image where you know that you have already detected the object, and this speeds up and removes the ambiguities in the object detection, but also the other way around. So object detection can help reconstruction, because when you do the bundle adjustment for the post-graph optimization, you can basically add, in addition to the scene-to-scene, so frame-to-frame correspondences, an additional set of correspondences that are given between, let's say, the points that you match from each frame of your scene and the object database. So you kind of have like more constraints for the bundle adjustment, and they show that this is able to improve the post-graph optimization and get better poses against drift. In general, there's a few works. I want to go into details. One of the main trend, anyway, is more related to the computer graphics application scenario, where, for example, you want to use 3D object retrieval in order to retrieve from a certain reconstruction of a scene CAD models from a huge database. So you can, for example, use key point detection and matching. In this case, they're using 3D Harris, which is a key point detection that's also available in PCL, to retrieve CAD models and then try to build up a sort of a virtual environment that is consistent with the scene, both in terms of object categories as well in terms of object poses. So the pose of the object that they retrieve should be consistent with respect to the environment that they build throughout a SLAM reconstruction algorithm. And then this is also very interesting work, which is called semantic frame. In this case, it's a similar idea, but they also added in the interaction with the user. So the user can basically touch the environment and say, for example, what is a certain category of objects like chairs, or what is a certain set of instances of objects like bananas or fruits. So the user can basically touch part of the environment, and then the algorithm will just use segmentation. Let's say it will merge together segmentation with semantic and make semantic segments that are consistent throughout the scene. The starting point for our work was kind of to also use this kind of reconstruction and SLAM algorithms to build up some reconstruction and extract semantic. The first thing we wanted to do is to just get segmentation. So segmentation in the sense of connected components. There's a lot of different segmentation algorithms. There's a lot of very efficient algorithms for range maps, and Alex also did a great work in PCL with a very cool RGBD segmentation algorithm, but they only work on 2.5D data, so only range maps. There's a few algorithms that work on point clouds, so full 3D point clouds, but they are extremely slow. So our idea was to build an incremental reconstruction and segmentation framework, so that at the end you can get something like this in terms of output. So you have a reconstruction framework, use like a SLAM pipeline. In this case, we use a pipeline for SLAM based on the concept of surface, which is kind of a extension of Kinect Fusion to point cloud SLAM. So instead of using voxels, use points that are associated with additional attributes, such as, for example, the variance and the confidence associated to each point. So this is the output that we want to get. In our approach, we use SLAM, and then in addition to the SLAM, we plug in a certain set of stages in order to update at every new frame a global segmentation map, which instead of having a representation for the geometry, also contains a representation for the points. I cannot go into details, of course, about the techniques that we are applying, but I just want to show you the results. One important attribute of our method is that compared to standard segmentation approaches that of course grow linearly with the size of the point cloud that they need to segment, in our case we are completely constant because we only update the global segmentation map based on the Froston so based on the current visible points, rendered over arrangement. So in that case, even if the global map is huge, because you're building up a large-scale environment, you only need to update at every new frame always the same amount of information, which makes the algorithm completely independent from the size of the map, so we can run it in real time. There's a nice video that we proposed last year at IROS, but I think the live demo is going to be more interesting. This is just to give you an idea of what we can get. So once we got these results, then the idea was, okay, this seems really, really cool in terms of some kind of rich information that we can use for something, let's say, a little bit higher in terms of semantic information that we want to extract. So the next step was to add object detection on top of that, and this is what we did. So we added a recognition module that could somehow enable object recognition and 3D pose estimation in real time based on this incremental reconstruction segmentation module, which is also the demo that Keisuke will show you in a few minutes. In this case, the main idea, the goal that we wanted to reach is to solve this kind of environment. So this is kind of a nightmare for most perception tasks, in the sense that you have RGBD sensor that cannot get specular surfaces that is used in these environments, which is like mostly made of metal, for example here in the sink. And then you have like objects that are very similar one to another, so basically the same object, just like a slightly different size. They're completely textureless, most of them are specular, are made out of metal or ceramics. And you want to not only recognize their identity, but also detect nicely the 3D pose, and also avoid false positives. So let's say that this approach is able to solve this kind of perception problems, mostly because it leverages the possibility of having multiple viewpoints fused together. Of course, also here I won't go into details, not to bore you too much. What we did is to use global descriptors that are available in PCL. In particular, we use RCVFH, which is a global descriptor that also gives you a local reference frame. So once you match an RCVFH, you also have for free a local reference frame that can be used to automatically estimate the 3D pose of every object. So I will show you in a while why the 3D pose is particularly important for this kind of application. It's in particular important. It's particularly relevant for augmented reality application. One thing that we do once we do the matching, we also do this kind of geometric verification, which is a very robust stage, in my opinion, that is able to remove most of the false positives. So what we do here is, since we use a Kinect Fusion, let's say, framework for this lambda construction, we have a TSDF in terms of representation for our points. And what we do is, once you have a pose provided by our CVFH or VFH descriptor, we can instead of computing the residual between the object with the current pose and the scene points, which means doing a lot of nearest neighbors, so that would be extremely not efficient. In this case, we directly access the TSDF elements, which kind of give you the distance from the surface, which allows you to compute the residual of your object model with respect to the scene very, very efficiently. So it's just a matter of accessing the right TSDF elements, and you can compute the residual. Why is the residual important? If you look at this chart, you can see that this is the number of views that we merge together, and this is somehow the distance of the descriptor, so the matching in the descriptor space and the matching using the residual. So you can see that the right object, which is this red curve here, becomes already the best. So you can remove a lot of ambiguities much earlier, so you really require a much smaller number of viewpoints when you merge them together if you use this residual approach, rather than in the descriptor space where things are, of course, more ambiguous, because these shapes are really, really similar. When you have like similar caps, for example, the global descriptor is, of course, going to be very, very similar in the descriptor space. So this is a very efficient approach to remove ambiguities, and also to be able to get the correct label for your object without creating a lot of frames, so without really needing to merge together a lot of viewpoints. So also here we did like an evaluation in terms of standard benchmark data set. Also here we are able to have a real-time algorithm that runs on Keisuke's laptop and is doing at the same time this LAM, so the reconstruction, the segmentation, the recognition, and also the visualization, so the rendering, which is also very GPU, let's say, intensive in terms of algorithm. This is just to show you some results, but then Keisuke will show you a way more interesting demo. But just to show you that we are now able to solve this kind of scene, so you know this will be very, very hard if you have only one viewpoint, so in standard object detection scenarios. And by just merging together appropriately these views, then you're able to see the labels that are correctly placed. There's no false positive, and also the local reference frame, which is basically the 3D pose estimated for every object. This is another scenario where I was, let's say, as I said, there are very, very similar objects on a metallic surface, which gives you extremely noisy points. But I also wanted to show you why this pose information is important, because you can have this kind of augmented reality applications. So you can basically augment for example, a hat here, a flower here, coherently with the object. And in that case, you can also do some kind of 3D occlusion of the rendering. So when you have an object in the foreground that occludes the 3D augmentation, you can properly occlude it because you have the entire knowledge of the geometry of the scene. Okay, I think that we can move on with the demo.
Plug it in.
Oh, I see.
Yes, this one.
Oh, I'm sorry.
No worries. Just I'll fix it up.
Maybe, yeah.
Do you need to plug in the charger?
Oh, it's okay, no problem. Yes. Okay.
Your working resolution.
The resolution is very, very small. Okay. I see.
Okay.
Yeah.
Go with that.
Maybe okay, fine. I guess. I hope. Okay, you can see. Yes, I'm showing the reconstruction demonstration for now. So, yeah, the object is placed on the chair, something like this, and yeah, scene is something like this. So, okay. Excuse me. Sorry. So, yeah. So, this is a normal image of the input text image, and this method is studying the reconstruction and also simultaneously segmentation. The color is the same segment, and also the global descriptor is computed on each segment, and the segment is matched against the text an object database, and you can see this character is object label, so sender is a sender, and the kernel is a kernel, it's a factory layout. And this method can estimate the object pose using the local reference frame, so we can put the object CZ, something like this. so for override on top of the CD, on top of the cup, and also put the hood CD on top of the sandal. Yes. And this that's it.
So, any questions for our speakers? Okay.
So you mentioned that you're doing verification on the TSDF distance instead of using your snipper.
Yes.
Have you noticed, like, the one problem depending on the reconstruction technique is if you're not really close to the surface, aren't the numbers often like very, very bad for the TSDF? Or is it still?
You mean it cannot be reconstructed in the thin shape, right? You mean? Yeah, it's same problem. Yeah, also this. Yeah, that's it.
But also in this case, consider that we're not looking for very good fit, absolute fit to the segmentation, but it's, you have to get a residual that's lower than the other shapes. So if the other shapes cannot be, let's say, fitted very well in the seam, that's already enough to get the correct protection.
Any more questions? Well, then I would say let's give a big round of applause to Federico and Keisuke.